Thanks for joining me today. We are going to go into some things about forces. These specifically are going to be forces that are inside of atoms and also around atoms holding other molecules together. So let's look at the questions we're going to try to answer today as I go through this. I'm going to say what forces hold atoms and molecules together. That's kind of our big question. And within that, there's a couple of different types of forces, different groups of forces. Some of them we will call intermolecular. The others we will call intramolecular. You can see the prefixes are a little bit different there. So we're going to talk about a number of different forces, try to classify them into each of those groups and give some characteristics of each. A lot of vocabulary with this one. So intermolecular, intramolecular, ionic, covalent, polar, nonpolar, and an alloy. So let's get to it. So to begin with, let's look at the difference and similarities between inter and intramolecular. They have different prefixes. These are good words to know or good prefixes to know just in general to help you with other words. Inter generally means something, between. So we have an interstate highway. That is a highway going between a couple of states. So typically when we put this in front of a word, we're talking about two different things being joined somehow. Excuse me. Intramolecular means within. Some of us have had an IV that stands for intravenous, and the venous is for a vein. That means within something. So when we use the prefix here, intramolecular, intramolecular is going to be inside of the molecule. So we're really just talking about one group of atoms at that point. Right? So a couple of other words here for inter to help you remember. Internet connects different locations, interstate, connecting some states. Interrupt is when someone breaks up a couple of conversations. Intra, you don't use as much, but it typically means inside. It's used a lot in medical jargon. Intracranial mean what inside of your head. And some businesses even have a thing called intranet, which is kind of like an internet, but it doesn't really leave the building. It just kind of stays within the company. Okay. So we're going to look at a bunch of examples. So very vocabulary laden with what we're going over today. So we're going to start with intramolecular forces. This is some of the things we've already been talking about up to this point. These are the things that actually hold atoms together. So they hold an atom to one another. This is what's going to make compounds. This is what's going to make molecules. If you look at the pictures on the right, these are some of the examples that we would have with that. We got three types: ionic, covalent, metallic, which I'll go into more detail here in just a minute. What they're going to be doing is holding an atom together. You can see it an ionic bond. This is what makes Na and Cl, turns into sodium chloride. So we're talking about the intramolecular force that holds the sodium to the chlorine to make the sodium chloride compound and the sodium chloride molecule. So if we start with ionic bonds, we've gone over these before. Typically, when we see an ionic bond, we have a positive and a negative combining. Often it's a metal or a non-metal. Sometimes it could be a group of atoms like this polyatomic. The image you have on the right would be of sodium chloride, which is your table salt. When we have these kinds of bonds, they are going to be the strongest bonds that we have. It's very difficult to pull these apart. Now, one thing to just illustrate in the images that we have over here, if you could see table salt up close, they actually don't have these little lines and these little sticks between them. We use these little lines and sticks to be able to represent the bonds and the forces that are holding them together. So when we say an ionic bond, like literally this line is supposed to be the bond. In reality, it probably looks a lot more like the middle picture where there's not any real sticks. Notice you've got these greens that are the chlorine, you've got the reds that there's sodium. Sodium's a smaller atom. And they would just kind of fit together. And again, the reason why they're going to be fitting together like this has to do with the positives and the negatives. It's in a very, very tight bond. And again, it's going to create a really high temperature required to melt, also, or boil even. So if we have a sample of table salt, for instance, you can put it in your oven and it's not going to melt. If you put sugar in the oven, typically that's going to happen because sugar is not ionic. Most of our ionic bonds tend to make very brittle solids. They turn into crystals and powders, and they would look a lot like table salt would look. One of the other characteristics is if we put it in water and dissolve it, it's going to be able to conduct electricity. Think about having the pluses, and I left out the minus here. But if we have a plus and a minus, again, that's what the sodium and the chlorine happens to be. The sodiums are positive, the chlorines are negative. If we put them in water, we're kind of creating positives and negatives. Should make it easier for the electricity and the electrons to flow between. And sometimes we see this phrase right here, a crystal lattice. This word lattice reminds me of a ladder, which is kind of what this picture on the left looks like, except it's more of a three-dimensional, kind of like a scaffolding when people are doing construction. So when we get an ionic bond and we get these positives and negatives, they tend to form these repeating geometric patterns, if we could be able to see them. Sometimes they're idealized like they are on the left. Sometimes they're idealized like they are here on the right. But if you see the term crystal lattice, it's essentially just talking about how do the pluses and minuses arrange themselves in an ionic bond. Okay. A second type of intra that we've talked about how to build a molecule is a covalent bond. This is typically when we have nonmetals. These, because they have lower boiling points and lower melting points, a lot of these are liquids and gases. They don't conduct electricity when we put them in water. Because they're sharing electrons, sometimes they share equally, sometimes they don't. We have the words polar and nonpolar for that. So if it's polar, typically what we're going to see is that the electrons get pulled to one end or one side a little bit more than the other one. Water is kind of a good example of that. Oxygen would win the tug of war a little bit better than hydrogen. So the electrons tend to stay over on this side of the entire molecule. So if you think about this whole thing, the negatives tend to be over here a little bit more, which makes this side a little bit negative. And if that side's a little bit negative, then this side becomes a little bit positive. And that's simply what polar means. It means that we're going to have differences in positive and negativity on opposite sides. A number of molecules are nonpolar. They share equally with one another, or they kind of close to equally, and we wouldn't see the pluses and minuses. And because of that, they have some different characteristics in how they behave. Diatomic molecules that we've mentioned before, like chlorine gas, hydrogen gas, oxygen gas, those tend to be nonpolar because they pull equally. And then there's some other things like carbon and hydrogen, even though they're not the same, they tend to have a pretty similar pull on the electrons. And a carbon and hydrogen bond in and of itself typically is not very polar. A third type we haven't talked about before is a metallic bond. Metallic bond occurs in, as the name looks like, in metals, things on the periodic table like gold and aluminum, and also alloys, which is a mixture of metals, things like brass. And what we see with them is they kind of get held together because the negative electrons tend to move around. They kind of hop from atom to atom to atom. And because the core of the atom stays positive and you have all these moving negative electrons, they're going to be attracted to its neighbor, or attracted back to the atom itself. And that tends to kind of hold the entire group of atoms together so that we see metals forming kind of in a clump or a nice solid. Let's switch gears. This is the intermolecular forces. These are the forces that are holding different molecules together. This is a force that is between the molecules. So they hold one molecule to another. This kind of helps explain, why does water stick to water? Why does it make a big drop? Why, not just one atom or one molecule, but why do we have a bunch of them, and why do they not separate from one another? So there's several different types of intermolecular forces. The strongest ones, again, are when we have a plus and a minus. So if we have a covalent molecule, particularly a polar covalent molecule, oftentimes we're going to have forces that are holding those polar covalents together. One of those is called a dipole-dipole interaction. Dipole, literally, we're using the prefix di, which means two. Pole means our ends. And so when we have a dipole, we've got two poles. And if you look at this example of hydrogen and chlorine, chlorine kind of wins the tug of war on the electron and becomes a little bit negative. Hydrogen tends to lose it and become a little bit positive. So when a hydrogen and chlorine, which is hydrochloric acid, comes close to another neighbor, the opposite ends tend to be attracted to one another because there's a negative and there's a positive. This happens again when we have a polar molecule. We have a polar molecule, you have positive and negative sides, and they're going to also attract their opposites when they come in contact with them. So an example, again, hydrogen is slightly positive and it's going to be slightly attracted to the negative end. This is a pretty strong intermolecular force. In other words, these things are going to be held together pretty tightly. There's a specific kind of dipole-dipole interaction called a hydrogen bond. As you might imagine, it has a hydrogen in it. And more specifically, it's when hydrogen is kind of having a dipole with oxygen, nitrogen, or chlorine. These are three of the most electronegative atoms that we have, which means that they're going to be winning the tug of war pretty easily. And so this is kind of similar to the previous slide, but it's going to happen specifically when we have hydrogen. Again, you'll notice in the picture up here, the oxygen becomes a little bit negative, so the hydrogen becomes a little bit positive. And so when we put a water molecule near another water molecule, they're going to align so that the opposite sides tend to attract one another. Okay. So again, this slide and the previous one are basically the same thing. This was just a more specific type that we have. All right. This is the strongest of all the intermolecular forces. And there's this thing called a dispersion force. This is pretty weak. we don't spend very much time on it at all. It is simply a temporary attractive force. Because the electrons are always moving around, sometimes they randomly pack on one side more than another. That's going to make this side more negative and attract a positive, just like it would in the previous two slides. However, it's not going to stay this way. Because these electrons move, this attraction is going to be very short-lived, and so because of that, it tends to be a very weak force that we have. So that's basically it. Lots of vocabulary to kind of keep straight. But in summary, forces, these are things that hold the atoms and molecules together. They can be intramolecular, and that's what's going to hold an atom to another atom. That's what's going to make our molecules and compounds. Or they can be, this would be ionic, covalent, and metallic. Or they can be intermolecular, which is going to be between two separate molecules and being able to try to hold those molecules together. Those can be our dipoles, our hydrogen, and our dispersion. Thanks for joining me.